part B of the same problem. But before we start solving part B, before I tell you what part B is, let me remind us what we have accomplished in part A. We had a ball on a massless string, and I brought it to some angle theta naught with vertical. I let it go. The ball goes. It hits a block of a given mass. This collision is on a frictionless surface, and then this ball sticks to the block, and they move up together. What we did, we found the height. How high will they go together? For part B, we have a different situation. For part B, I start the same way. Same ball on the same string. It hits the block. But now the difference is that this collision is perfectly elastic. They are not stuck together. They just collide, and they tell us that the collision is perfectly elastic. Now, this ball, instead of ball and block going up, so that's not true anymore. Instead of going up, now this ball bounces back. Bounces back. This is not up to scale for sure. And the block will also move after this collision. So the question is, I need to write enough equations to be able to solve for this height that this ball will make. Editing. I need to, what do they ask us to find? We need to write the equations, enough equations, that could be solved to find how high will this ball go after the collision. So we again are solving for this height, but the collision is now different. It is perfectly elastic. How we will solve this problem? First of all, do we remember what is an elastic, perfectly elastic collision? Yes. If they tell us that the collision is perfectly elastic, we know that it means by definition the kinetic energy is conserved in this collision. So how do we start? We again need to split this problem into several problems. The beginning is the same. We use step one, we use conservation of mechanical energy to find conservation of mechanical energy U1 plus kinetic energy 1, U2 plus kinetic energy 2. We will use conservation of mechanical energy to find the velocity of this ball right before the impact. Now, after that, we will use conservation of linear momentum. Px before is equal to Px after. In addition to this equation, now we know that since the collision is perfectly elastic, the kinetic energy before the collision is the same as kinetic energy after the collision. And now, after we find velocities of both of this block and the ball after the impact, we again can use conservation of mechanical energy to find how high will it go. So my last equation will be conservation of mechanical energy again. Sounds like a plan? Let's implement this plan. This is point 1. This is point 2. We have U1 from previous problem, MB, G, L, 1 minus cosine theta naught. We already calculated it in previous problem. This is my U1 potential energy right here. Kinetic energy here is 0. I let it go. Now I write potential, point 2, potential energy of this ball right before the collision. It is 0 because it is on the surface. And what is kinetic energy? We wrote it as m ball and then v ball squared over 2. This is the kinetic energy. Okay, this is my first equation. Now we are ready to write the second equation, conservation of linear momentum. What is total momentum of the system right before the collision? It is mass of the ball, velocity of the ball, which is VB, and the projection is positive because the ball is moving along positive x direction. And the box is at rest, so this is total momentum. We are done with the left-hand side of this equation. What is px after? Now the ball is moving to the left, so projection of linear momentum of the ball is negative now. I put minus mb. What is the velocity of the ball? How we will denote it? After the collision, I will add this prime. So this is just prime, indicated that this velocity is the velocity of the ball after the collision. And the box is also moving. The box will be moving to the right. Its momentum will be positive. So I have m1 and then unknown velocity of the box. How do we call it? I will call it v1 prime, where index 1 stays for the box, belongs to the box. Okay, one more equation. Kinetic energy before is equal to kinetic energy after. What is the kinetic energy before the collision? All we had this ball moving. So what is its kinetic energy? This is mb. What is the velocity of the ball right before the impact? It was v ball squared over 2. This is the kinetic energy before the collision. Kinetic energy of the box is 0, it is at rest. What is kinetic energy of both objects after the collision? It is mb vb prime squared over 2. This is the kinetic energy of the ball after the collision. And then we need to add the kinetic energy of the box after the collision. All right, so this is kinetic energy before is equal to kinetic energy after. And now our last equation will be again conservation of mechanical energy for the ball. So the ball is now moving up. Potential energy here on the surface is 0. We have non-zero kinetic energy, which is m ball. What is the velocity after the impact? v ball prime squared over 2. This is the kinetic energy of the ball. This is u1. This is kinetic energy 1. u1 is 0. Kinetic energy 1. We just wrote it. And this is equal to u2. What is point 2 now? It is this point. This is point 2. So how high will it go? What is potential energy there? It is m ball g and unknown height h. Unknown height h. All right. So do we have enough equations? I don't know. Let's count our unknowns. I have 4 equations, but how many unknowns do I have? I do not know velocity of the ball right here. I don't know the velocity of the ball right before the impact. I don't know the velocity of the ball right after the collision. I don't know the velocity of the box right after the collision. And I don't know h, height. That's what I'm looking for. How high will this ball go? Look at this. I have 4 unknowns and 1, 2, 3, 4 equations. Number of equations is equal to this number of unknowns. We can solve for h. I will not do it. It will be long calculations. But what they ask us to do, they ask us to write enough equations to be able to solve for h. And we did it.